Every day of your life is spent at the absolute bottom of a massive, heavy ocean of gas. We do not usually feel it, but the air above us has mass, and gravity pulls it down. That continuous column of air presses uniformly on every surface it touches, creating a physical weight known as atmospheric pressure. Measuring this invisible weight requires a mathematical model that accounts for fluid density and gravitational force. Once established, this framework allows us to calculate the specific physiological limits of the human body, such as the maximum depth from which we can draw water through a straw. The same laws of fluid statics that govern the movement of the open atmosphere also dictate the internal mechanics of the human respiratory system. To capture and quantify this atmospheric weight, 17th century physicists developed the Mercury barometer. This diagram illustrates several early historical designs. While their shapes vary, each is engineered to trap a fluid column against the surrounding atmospheric pressure. A standard barometer consists of an open mercury reservoir at the base and a sealed glass tube rising vertically from it. The liquid in the tube rises because the atmosphere is pressing down on the exposed mercury in the reservoir, forcing it upward into the vacuum of the tube. In this system, the height of the liquid column serves as a direct, measurable counterweight to the invisible atmosphere. This relies on the principle of hydrostatic equilibrium. In a static fluid, any 2 points at the same horizontal level experience the same pressure. These physics notes map that theory to a real-world calculation. Point 3 is located on the surface of the pool, exposed to the air, meaning its pressure equals the local atmospheric pressure, PA. Point 2 sits at the same level inside the tube. Its pressure is the sum of the vacuum at the top, which is 0, and the weight of the mercury column pressing down on it. The pressure exerted by that column is defined by the hydrostatic equation, the fluid's density, ρm, multiplied by gravity, g, and the height of the column, h. By setting the pressure at point 3 equal to point 2, we find that atmospheric pressure equals the density of mercury times gravity times height. At sea level, we insert the known constants for atmospheric pressure, the density of mercury, and gravity. Solving for h, the equation predicts a column height of exactly 76 centimeters. The 76 centimeter mark represents the precise mathematical equilibrium where liquid density balances the weight of the atmosphere. This same equilibrium governs the biological action of drawing water through a straw. While it appears that the mouth is pulling the liquid upward, biological suction does not involve an active pulling force acting on the fluid itself. Instead, the lungs expand to create a zone of low pressure, a partial vacuum, inside the body. The liquid is driven up the straw by the higher atmospheric pressure resting on the cup's surface, which overcomes the lower pressure inside the lungs. Consider a specific case. If a boy uses his lungs to reduce his internal pressure to 750 millimeters of mercury, we can calculate the maximum depth of water he can drink. We apply the balance equation. The pressure at the surface of the cup equals the pressure in the lungs plus the pressure of the water column. While the internal pressure is measured in equivalent millimeters of mercury, the fluid being lifted is water. To equate these, we insert the hydrostatic formula for mercury on both sides to account for the pressure values. Since gravity acts equally on all components of the system, the term cancels out, simplifying the calculation. We group the mercury terms to isolate the pressure differential, a height difference of 1 centimeter of mercury, on the left side. Inserting the specific densities, 13.6 for mercury and 1 for water, finalizes the ratio. The result shows that the maximum height of the water column the boy can support is 13.6 centimeters. This result confirms that the limits of human suction are determined by the fixed constants of fluid statics. This comparison highlights why the atmospheric push supported a 76 centimeter mercury column, yet the boy's lung pressure differential only moved water 13.6 centimeters. This height discrepancy is a direct result of density. Mercury is 13.6 times denser than water. If a barometer were filled with water instead of mercury, the atmosphere would support a column over 10 meters tall. Density dictates the physical scale of all hydraulic systems, from global atmospheric movements to the internal flow of the human body. The ability to drink through a straw is entirely dependent on the weight of the air above us. The equation P equals rho times G times H remains constant, whether calculating the pressure of a dense metal or life-giving water. This perpetual quest for equalized pressure bridges the mechanics of the open atmosphere directly to the interior of our own lungs.